Deep within the cosmic abyss, a silence once reigned, absolute and terrifying. For decades, these celestial devourers, black holes, were thought to be the ultimate prisons of the universe, consuming all that crossed their event horizons, never to release a single photon. They were the perfect cosmic vacuum cleaners, erasing existence without a trace. Yet, in 1974, one of the greatest minds of our time, Stephen Hawking, unveiled a truth so unsettling it threatened to unravel the very fabric of physical law. Black holes, he proposed, were not truly black. They slowly, imperceptibly, radiate energy back into space, a phenomenon now known as Hawking radiation. This revelation, profound as it was, immediately ignited a crisis. The Hawking radiation, it seemed, was entirely random, a thermal hiss devoid of any discernible pattern or memory. This presented a catastrophic problem. If a star, perhaps 100 times the mass of our Sun, collapsed into a black hole, every atom, every subatomic particle, every unique quantum tremor that made up that star would be swallowed. That star carried an immense, almost infinite library of information about its composition, its history, its very structure. Consider a single grain of sand on a beach, its shape, its crystalline structure, the specific atoms it is made from, its exact position, all represent a unique piece of information. Now, multiply that by the uncountable quadrillions of particles in a star, and the scale of the lost data becomes unimaginable. According to the ironclad laws of quantum mechanics, information cannot simply vanish from the universe. It can be transformed, rearranged, scattered, but never truly destroyed. Yet, if Hawking radiation was truly random, then all that unique, complex information about the star, its very identity, would be permanently erased as the black hole evaporated. This wasn't merely a minor inconsistency, it was a flagrant violation of a core tenet of quantum theory, a fundamental principle of reality itself. This created what physicists called the information paradox, a profound cosmic dissonance at the very intersection of general relativity, the theory of the very large, and quantum mechanics, the theory of the very small. It was a theoretical firewall, threatening to burn down the entire theoretical landscape. The scientific community fractured. Stephen Hawking, initially, championed the idea that information was indeed lost, accepting the profound implications. But other brilliant minds vehemently disagreed. Physicists like Leonard Susskind, known for his passionate and often theatrical arguments, and Gerard Tooft, a Nobel laureate, stood firm, arguing with unwavering conviction that information must be preserved. To them, the universe simply could not operate in a way that destroyed fundamental data. The debate wasn't abstract. It reached the highest levels of theoretical physics, spanning decades and captivating the imaginations of scientists worldwide. Was reality fundamentally deterministic, or could information truly be annihilated? This was a question about the very nature of cause and effect, of what it means for something to exist. This deep cosmic dissonance, this missing song in the universe's grand symphony, became the primary motivation for a radical new idea, a desperate, elegant attempt to restore harmony. To solve this seemingly unresolvable contradiction, physicists were forced to look beyond the long-held belief that the universe's fundamental constituents were point-like particles, tiny, dimensionless dots. The information paradox acted as a crucible, forging a new paradigm. It demanded a much stranger, more musical alternative, one that promised to reconcile the irreconcilable and provide a profound, new understanding of existence. The quest to silence this unsettling cosmic silence, to find the black hole's missing song, was the very impulse that would lead them to reimagine the fundamental building blocks of everything. In the deepest reaches of the cosmos, the universe sings, not with a noise that can be heard by human ears, but with a profound, hidden resonance that dictates the very fabric of reality. To truly grasp the strangest theory in modern physics, we must first journey back over 2 millennia, not to the cacophony of a collapsing star or the quantum paradoxes of black holes, but to the sun-drenched Aegean Sea, to the enigmatic island of Samos, around 500 years before the Common Era. This is where a radical idea, echoing through history, first took root in the mind of a philosopher and mathematician named Pythagoras. Consider the simple act of plucking a string. A musical note rings out. Change the length of that string, and the note shifts, its pitch rising or falling. It was in the mystical and mathematical school established by Pythagoras and his devoted followers that this seemingly straightforward observation unlocked a universe of profound connections. Using an unassuming instrument known as a monochord, a single string stretched over a resonating box with a movable bridge, the Pythagoreans made a discovery that would forever alter humanity's perception of order and chaos. They meticulously observed that specific, harmonious musical intervals, those sounds that strike our ears as perfectly consonant, were directly linked to simple, elegant mathematical ratios of the string's length. A string shortened precisely by half produced an octave, a ratio of 1 to 2. Divide it by 2/3 of its original length, and you hear a perfect fifth, a ratio of 2 to 3. And at 3/4 its length, a perfect fourth, a ratio of 3 to 4. This was not mere coincidence. It was a revelation that mathematical beauty underpinned the harmony we perceived. If the pleasing sounds of music were governed by such simple, beautiful numbers, the Pythagoreans concluded, then surely the entire universe, the grand cosmos itself, must also be an ordered, harmonious system, a celestial symphony governed by these very same numerical relationships. This breathtaking concept became known as Musica Universalis, the music of the spheres. It posited that the planets, the sun, and the moon, in their majestic orbits, moved not randomly, but in paths defined by these precise musical ratios. Their continuous motion, they believed, produced a cosmic symphony, a melody so perfect, so omnipresent, that it transcended human perception. It was a harmony too sublime, too fundamental for our limited ears to register. This was no fleeting philosophical fancy. The Pythagorean ideal of a numerically harmonious universe permeated Western thought for centuries, shaping the minds of towering intellects. Plato, the Athenian philosopher, was deeply influenced, weaving these ideas into his cosmology described in the Timaeus, where the soul of the universe was constructed according to musical proportions. Over 2 millennia later, in the early 1600s, the brilliant German astronomer Johannes Kepler became utterly obsessed with this ancient quest. He spent years of his life, with an almost spiritual devotion, trying to discover these precise celestial harmonies within the planetary models he was meticulously developing. He believed, with unwavering conviction, that the elliptical orbits he had painstakingly uncovered must somehow resonate with the very same perfect ratios found on Pythagoras's monochord, seeking to tune the solar system like a colossal cosmic instrument. The modern concept of string theory, with its vision of vibrating fundamental filaments, is not some bizarre, isolated invention of the 20th century. Instead, it emerges as the latest and most exquisitely sophisticated chapter in this millennia-long human odyssey. It is a direct intellectual descendant of the Pythagorean monochord, a continuous, unwavering quest to uncover a hidden, simple, and profoundly musical order underlying the bewildering complexity of the universe itself. What happens when science makes a colossal mistake, a brilliant idea that is beautiful yet utterly wrong for its intended purpose? Sometimes, from the ashes of such failures, a seed is planted that, against all odds, blossoms into the most radical new understanding of reality. This is precisely where the modern story of string theory truly begins, not with a grand revelation, but with an accidental discovery born from a time of profound chaos in particle physics. Travel with us back to the late 1960s, a period that physicists often recall as the particle zoo era. Particle accelerators, like those at CERN in Switzerland or Brookhaven in the United States, were smashing atomic nuclei together with unprecedented force, revealing a bewildering menagerie of new, exotic particles. There were hundreds of these so-called hadrons, particles like protons, neutrons, and their more ephemeral cousins, appearing in the experimental data, each a unique tremor in the quantum fabric. Yet there was no overarching theory, no grand organizing principle to make sense of this chaotic multitude. It was like discovering a vast, vibrant ecosystem filled with creatures, but having no map, no evolutionary tree, no idea how they all related to one another. Amidst this confusion, physicists were desperate to find the elusive theory that described the strong nuclear force, the most powerful of nature's four fundamental forces, the cosmic glue that binds atomic nuclei together, holding the universe from collapsing into a formless goo. It is the force that allows stars to burn and elements to form. Without it, there would be no atoms, no chemistry, no life. So the stakes were incredibly high. Then, in the year 1968, a young Italian theoretical physicist named Gabriele Veneziano, working at the European Organization for Nuclear Research, known by its acronym CERN, was painstakingly sifting through mountains of data from these high-energy particle collisions. He was searching for a mathematical pattern, a hidden formula that could describe the intricate dance of these colliding hadrons. To his utter astonishment, Veneziano stumbled upon a 200-year-old mathematical formula, a forgotten relic of pure mathematics, the Euler beta function. This obscure piece of elegant mathematics, originally conceived by the brilliant Swiss mathematician Leonhard Euler in the 18th century, seemed to perfectly, almost magically, describe the scattering behavior of these tiny, energetic particles. It was an uncanny fit, a profound and inexplicable congruence between an abstract mathematical tool and the raw data of the subatomic world. No one understood why a formula from the era of horse-drawn carriages could possibly predict the behavior of particles moving at near the speed of light. It was a piece of magic mathematics, a tune without an orchestra. The profound mystery of Veneziano's formula lingered for 2 years. It was not until 1970 that the true physical interpretation of this accidental discovery finally came to light, independently unveiled by 3 brilliant minds: Yoichiro Nambu of the University of Chicago, Holger Beck-Nielsen of the Niels Bohr Institute, and Leonard Susskind of Stanford University. They realized, with a flash of insight that would reshape physics, that Veneziano's formula was not describing point-like particles at all, those dimensionless dots that had formed the foundation of physics for centuries. Instead, the formula described tiny, one-dimensional vibrating filaments of energy. Strings. This radical notion, dubbed hadronic string theory, was immediately hailed as a potential breakthrough. The idea was compelling. Just as a vibrating guitar string can produce different musical notes depending on how it vibrates, these fundamental strings, vibrating at different frequencies, could give rise to all the various particles observed in the particle zoo. Each particle, from an electron to a proton, was simply a different note played on a fundamental string. This was a profoundly elegant, almost poetic vision, promising to bring harmony to the chaotic world of subatomic particles. However, this promising new theory, born from a lucky accident, quickly revealed its fatal flaws. One glaring problem was its unavoidable prediction of a massless particle with a spin of 2, a theoretical entity that did not, and could not, exist within the context of the strong nuclear force. No known hadron possessed these characteristics. It was like a beautiful symphony that included a note no instrument could play. Even more bizarre, and perhaps even more damning for a theory aiming to describe our reality, was its mathematical requirement for an impossible 26 dimensions of space-time. Our universe, as we perceive it, exists in 4 dimensions: 3 of space, up and down, left and right, forward and backward, and 1 of time. The notion of 22 extra spatial dimensions, unseen and unfelt, was simply unfathomable and deeply inconsistent with every observation of our world. How could a physical theory demand such an alien reality? By the mid-1970s, the dream of hadronic string theory had all but evaporated. A new, more successful theory, quantum chromodynamics, or QCD, emerged, proving to be the correct description of the strong nuclear force. QCD precisely explained the behavior of hadrons and the fundamental particles they are made of, quarks and gluons. With the success of quantum chromodynamics, hadronic string theory was abandoned. It was widely considered a fascinating but ultimately failed footnote in the history of physics, a beautiful mathematical curiosity that simply did not describe our universe. Its few remaining proponents, clinging to the elegance of its core idea, were left largely isolated, wandering in the scientific wilderness, their radical vision dismissed as a theoretical dead end. The music of strings, it seemed, had stopped playing. A theory once relegated to the dustbin of scientific history, deemed a beautiful but broken melody, refused to be silenced. In the late 1970s and early 1980s, while the broader scientific symphony moved on, a quiet, insistent hum persisted within a small, determined chorus of physicists. They were the outliers, the unwavering few, who believed the failed tune of string theory still held a profound, unheard harmony. To them, the universe had not yet revealed all its secrets, and this discarded idea was far from finished. Among these tenacious individuals were John Schwartz from the California Institute of Technology and Michael Green from Queen Mary University of London. To many, the theory's biggest flaw, a problematic massless particle with a spin of 2, was a death knell. This theoretical entity simply did not fit into the established understanding of the strong nuclear force, which string theory was originally attempting to describe. But Schwartz and Green looked at this theoretical anomaly and recognized an uncanny echo, a precise mathematical signature that resonated with a different, much grander aspect of physics. What if this particle, this ghost in the machine that made the theory inconsistent for its original purpose, wasn't a flaw at all, but the very particle they had been searching for elsewhere? What if it possessed the exact properties of the graviton, the hypothetical quantum particle of gravity itself? This was the audacious leap, the sudden shift in perspective that would redefine the entire endeavor. String theory, they dared to propose, was not a theory of the strong nuclear force as originally conceived. Instead, it was a breathtaking candidate for a theory of everything, a unified description of all forces, all particles, all of existence, including the elusive force of gravity that governs the dance of planets and stars. Such an all-encompassing theory, however, demanded a radical adjustment in scale. If strings were to describe reality at its most fundamental level, they couldn't be relatively large, like the protons and neutrons they were once meant to describe. They had to shrink, dramatically, to the almost inconceivable Planck length. Consider this: the Planck length is 10 to the power of negative 35 meters. To truly grasp that scale, imagine an atom, already infinitesimally small, magnified until it spanned the entire observable universe. Even at that colossal size, a string vibrating at the Planck length would still be no larger than a single strand of your hair. These were not mere particles. They were vibrational flickers at the absolute boundary of discernible reality, far smaller than even the nucleus of an atom, holding the potential to unify quantum mechanics with general relativity. Yet, even with this grand vision, the theory remained deeply flawed. Mathematical inconsistencies, often called anomalies, continued to plague its equations. Think of these anomalies as fatal bugs hidden deep within the cosmic code, glitches that would cause the entire theoretical framework to unravel, leading to nonsensical results like probabilities greater than 100% or infinite energy. For years, these mathematical time bombs threatened to detonate the entire superstring enterprise, making it seem impossible to construct a consistent theory that could accurately describe our universe without breaking down. The challenge was immense, demanding a solution that seemed beyond reach. Then, in the scorching summer of 1984, a scientific miracle unfolded. In a quiet, almost understated paper, Schwartz and Green unveiled a revelation that would ignite what became known as the first Superstring Revolution. They proved that in one very specific, meticulously constructed version of string theory, all the potentially lethal anomalies, those catastrophic mathematical contradictions, miraculously canceled each other out. It was as if the universe's internal debugger had found a perfect, self-correcting mechanism, leaving behind a pristine, anomaly-free theory. This was not a lucky guess. It was a profound discovery of an inherent mathematical elegance, a hidden symmetry that had evaded detection for years, finally revealing the true potential of strings. But this astounding mathematical harmony came with a startling price tag, a set of profound demands from the universe itself. Firstly, the theory only achieved this miraculous anomaly cancellation if it embraced a new, deeply elegant kind of symmetry known as supersymmetry. Supersymmetry posits that every known fundamental particle, from the electron that flows through your circuits to the photon that carries light, has an undiscovered superpartner, a heavier, subtly different twin particle. Electrons would have selectrons, photons would have photons, and so on. None of these superpartners have ever been definitively observed, making supersymmetry a bold prediction awaiting experimental verification by the next generation of particle accelerators. Secondly, and perhaps even more mind-bending, the theory demanded that our universe must possess not the familiar 4 dimensions of space-time, 3 of space and 1 of time, but a staggering 10 dimensions. 1 dimension of time and 9 dimensions of space. This raises an immediate, profound question. If these 6 extra spatial dimensions exist, why do we not perceive them? Why is our reality seemingly limited to the 3 dimensions of height, width, and depth that we navigate daily, with our senses seemingly blind to this greater cosmic expanse? The answer lies in a concept known as compactification. Consider a garden hose stretching for many miles. From a great distance, it appears to be a one-dimensional line. An ant walking along the hose, however, experiences 2 dimensions. It can move forward and backward along the length of the hose, but also around its circumference. The circular dimension, while real, is compactified, curled up so tightly that it is invisible from afar. In a dizzyingly similar fashion, the 6 extra spatial dimensions posited by string theory are believed to be curled up into incredibly tiny, complex geometric shapes, far smaller than the most fundamental particles we can currently probe. These dimensions are not missing, they are simply hidden, too minuscule for our perception, folded into the very fabric of space-time itself. They are the intricate, unseen architecture upon which the symphony of our universe is played, influencing everything without ever being directly observed. The thrill of discovery, the sudden flash of insight that transforms our understanding of the cosmos, often comes with an unexpected hangover. For string theory, the euphoria of the first superstring revolution, the revelation that a consistent, 10-dimensional theory could unite gravity with quantum mechanics, was short-lived. By the early 1990s, the initial excitement had given way to a profound sense of confusion, a scientific quandary that threatened to derail the entire project. Scientists had not found one unique, elegant theory of everything. Instead, they had stumbled upon a bewildering array of 5 distinct and equally consistent superstring theories. These were known by their technical classifications: Type 1, Type 2A, Type 2B, SO32 heterotic, and E8 cross E8 heterotic. Each of these 5 theories was mathematically impeccable, free from the deadly anomalies that had plagued earlier attempts. Each of them demanded a universe of 10 dimensions, just as predicted. But here was the crippling problem. They described fundamentally different universes, complete with varying sets of particles, forces, and fundamental interactions. It was as if physicists had been searching for the single, perfect blueprint of reality, only to discover 5 equally valid yet divergent designs. This was a deep disappointment, a bitter pill to swallow for those who dreamed of a singular theory of everything. Instead of a unique cosmic symphony, science was left with 5 competing orchestras, each playing a different tune, with no discernible reason to prefer one over the others. Was our universe a Type 2A world, with its specific symmetries and particle content, or was it a heterotic one, governed by a different set of foundational rules? The field entered a period of stagnation, a quiet despair settling over many who feared that string theory, for all its beauty and mathematical prowess, had once again reached an insurmountable dead end. The dream of unification seemed to crumble under the weight of its own abundance. But the entire landscape of theoretical physics was about to undergo a dramatic, almost unimaginable transformation. The year was 1995, and the stage was set at a pivotal string theory conference held at the University of Southern California. The air buzzed with anticipation, yet beneath it lay a current of uncertainty. Then, in a legendary lecture that would reverberate through the halls of physics for decades, Edward Witten, from the prestigious Institute for Advanced Study, and widely regarded as one of the leading physicists of his generation, stepped forward to propose a breathtaking new vision. His words were a scientific revelation, an intellectual earthquake that shifted the very foundations of the field. Witten presented compelling evidence, born from rigorous mathematical insights, that these 5 seemingly distinct string theories were not competitors at all. They were not independent blueprints for different universes. Instead, he argued, they were merely different approximations, partial glimpses, of a single, deeper, more fundamental underlying theory. He tentatively dubbed this mysterious, all-encompassing framework M-theory. The M itself was enigmatic, left open to interpretation, perhaps mystery, matrix, or even mother. What was certain, however, was its profound implication. M-theory lived not in the familiar 10 dimensions of the previously discovered string theories, but in an even stranger, more expansive 11 dimensions. To grasp this profound concept, consider a classic parable, one passed down through centuries. Several blind men encounter an elephant for the first time. One touches its sturdy leg and declares, "This is clearly a tree trunk." Another feels its long, flexible trunk and insists, "No, it is a giant snake." A third grasps its broad, flapping ear and proclaims, "You are both wrong, it is a massive fan." Each man is describing a part of the animal accurately from their limited perspective, but none of them perceives the entire elephant. The 5 string theories Witten proposed were precisely like those blind men. Each was a true description, but only of a specific aspect of the deeper, 11-dimensional M-theory. These 5 string theories were merely different perspectives one would get when looking at this 11-dimensional behemoth from different vantage points, or under specific mathematical conditions. What appeared as separate, conflicting realities were in fact unified, interconnected facets of a single, magnificent whole. This groundbreaking insight ignited what became known as the Second Superstring Revolution, a seismic shift that unified the previously fractured field of string theory. It revealed a hidden, majestic structure, suggesting that the true nature of reality was not just strange and 10-dimensional, but even stranger, more elegant, and profoundly 11-dimensional than previously imagined, a cosmic unity waiting to be fully deciphered. What if everything we perceive, every star, every galaxy, every breath we take, is nothing more than a cosmic illusion? What if the universe, in all its three-dimensional glory and the relentless march of time, is merely a projection, a grand, impossibly detailed hologram? While the pursuit of tiny vibrating strings or hidden extra dimensions continues to challenge the limits of our experimental capabilities, string theory, specifically its deeper incarnation known as M-theory, has unexpectedly gifted us with one of the most powerful and mind-bending concepts in modern physics. This radical new understanding, a surprising offshoot, has become an indispensable tool, a practical ghost from the very machine of reality. This journey into the holographic cosmos begins not with strings, but with the enigmatic nature of black holes. For decades, these cosmic behemoths puzzled the greatest minds, including the towering intellects of Jacob Bekenstein and Stephen Hawking. They grappled with a profound question: how much information can a black hole truly contain? Their groundbreaking insights led to a startling realization: the maximum information stored within any region of space is not proportional to its volume, as intuition might suggest, but to the area of its boundary, its surrounding surface. This was a concept utterly counterintuitive, yet eerily familiar. It was precisely how a hologram functions, encoding a three-dimensional image onto a two-dimensional surface, a flat plate that, when illuminated correctly, springs to life with depth and perspective. This was the nascent spark of the holographic principle. The idea, revolutionary in its simplicity, begged for a precise mathematical formulation. That arrived in 1997, courtesy of the Argentinian-American physicist Juan Maldacena. Building upon the foundational work laid by others, including Leonard Susskind and Gerard Hooft, Maldacena unveiled a stunning mathematical duality, an almost magical equivalence that sent ripples through the theoretical physics community. He discovered that a theory of gravity, explicitly including strings, existing within a specific five-dimensional, saddle-shaped spacetime, a peculiar geometry known as anti-de Sitter space, or ADS for short, was mathematically identical to an ordinary quantum field theory without gravity, a conformal field theory, or CFT, living on the four-dimensional boundary of that very space. This was a discovery of monumental proportions, akin to unearthing a cosmic Rosetta Stone. For centuries, the ancient Egyptian hieroglyphs remained an impenetrable mystery until scholars found the Rosetta Stone, which translated their complex symbols into familiar Greek script. Maldacena's correspondence did something remarkably similar for physics. It provided a dictionary, a profound translation mechanism between the notoriously difficult language of quantum gravity, with its elusive strings and warped dimensions, and the well-understood, experimentally verifiable language of particle physics. It was a bridge connecting two seemingly disparate worlds, showing they were merely different descriptions of the same underlying reality. The philosophical implications of this AD-CFT correspondence are nothing short of breathtaking. It hints at the possibility that our entire universe, with its vast galaxies, swirling nebulae, and the very ground beneath our feet, might be a holographic projection of information stored on a distant two-dimensional surface. Could our three-dimensional reality be an elaborate illusion, a vivid cosmic movie played out on a far-off two-dimensional screen? It is a question that challenges our most fundamental perceptions of existence. pushing the boundaries of what is real. But the ADS-CFT correspondence is far more than a mere philosophical curiosity. It has evolved into an incredibly practical calculational tool, a genuine powerhouse in theoretical physics. Physicists now routinely use this gravity quantum dictionary to tackle complex, real-world problems that, on the surface, appear to have nothing directly to do with string theory itself. For instance, it provides invaluable insights into the elusive, superheated quark-gluon plasma, a primordial soup of matter created in colossal particle accelerators like the relativistic heavy ion collider. This extreme state of matter, existing only for fleeting microseconds, mimics the conditions of the universe just moments after the Big Bang. Applying the ADS-CFT correspondence allows physicists to model its properties, such as its incredibly low viscosity, with unprecedented accuracy, translating the chaotic dance of quantum particles into the more manageable language of a black hole in a higher dimension. Furthermore, this correspondence is proving instrumental in condensed matter physics, offering new ways to model certain exotic states of matter. Scientists are using it to understand phenomena that defy conventional explanations, such as high-temperature superconductivity or the behavior of strongly interacting electron systems. It provides a novel lens, a different mathematical framework, through which to view and solve problems that have long stymied researchers. Even without a single vibrating string being experimentally detected, this theory, born from the ambitious quest for a unified understanding of reality, has undeniably provided a profound new grasp of the deep, intricate relationship between gravity and quantum mechanics. It stands as a testament to the immense value of string theory, not just as a grand theory of everything, but as a potent mathematical laboratory for exploring the very nature of reality itself. The universe, for all its majestic harmony, might be playing a tune far more complex, perhaps even unsettling, than we ever dared to imagine. For centuries, the very bedrock of scientific inquiry rested upon the fervent hope that a single, elegant set of laws would eventually reveal a unique cosmic blueprint, a lone masterpiece composed by mathematics itself. But string theory, the very framework that promised to unify all forces, has delivered a revelation that shatters that ancient dream, replacing it with a concept so vast, so bewildering, it forces us to reconsider our place in the very fabric of existence. As our understanding deepened, it became starkly clear that the elegant equations of string theory do not, in fact, produce a single, unique universe. We know that our reality is perceived in 4 dimensions, 3 of space and 1 of time. Yet the theory consistently demands a universe of 10 dimensions. This means that to reconcile string theory with the world we experience, those extra 6 spatial dimensions must be compactified, or curled up, into incredibly tiny, complex geometric structures, far smaller than even a single atom. These intricate forms are known as Calabi-Yau manifolds, named after the mathematicians Eugenio Calabi and Xing-Tung Yau, who pioneered their study. The challenge, and the profound twist, lies in the sheer number of ways these extra dimensions can be folded. Think of an incredibly intricate piece of cosmic origami. Mathematicians have calculated that there isn't just one way to perform this compactification. Instead, there could be at least 10 to the power of 500 different ways to fold these 6 unseen dimensions. To grasp the enormity of that number, consider that there are estimated to be only 10 to the power of 80 atoms in the entire observable universe. 10 to the power of 500 is a number so astronomically vast it utterly dwarfs any quantity we can conceptualize. Each one of these folding configurations results in a different vacuum state, a unique set of particles, forces, and fundamental physical laws. This immense, perhaps infinite array of possible universes is what physicists now call the string theory landscape. This discovery fundamentally reshaped the original ambition of string theory, which was to predict all the constants of nature from first principles, to derive, for example, the precise mass of an electron, or the strength of gravity solely from the theory's inherent logic. Instead, the string theory landscape suggests that our universe, with its very specific and life-friendly laws, is just one small valley in an immense cosmic terrain of possibilities. It implies a multiverse, not just as a philosophical idea, but as a direct consequence of the most promising candidate for a theory of everything. Our universe, perhaps, is merely one of countless pocket universes, each governed by its own unique physics, a different composition played on the cosmic stage. This leads directly to one of the most controversial ideas in modern cosmology, the anthropic principle. This principle suggests that we find ourselves in this particular universe, with its finely tuned laws that allow for the existence of stars, planets, and life itself, simply because we could not exist to observe any other kind. If the laws of physics were slightly different, if gravity were a tiny bit stronger, or the electron's mass a fraction heavier, the universe might be a barren, lifeless expanse, incapable of forming complex structures. Has string theory, then, replaced scientific prediction with a post hoc explanation? Does it transform fundamental physics from a predictive science capable of deducing the constants of nature into a kind of cosmic geography, merely mapping out the possibilities rather than pinpointing the unique reality? This profound shift has ignited an intense debate among the greatest minds in physics. On one side are proponents of the landscape, like the influential physicist Leonard Susskind, who argues that this vast array of possibilities is a natural and perhaps inevitable outcome of a truly fundamental theory. For him, the anthropic principle offers a powerful, albeit unsettling, explanation for why our universe appears so uniquely suited for life. On the other side are those, such as the Nobel laureate David Gross, who express deep concern. Gross fears that if string theory cannot uniquely predict the constants of nature, if it only offers an infinite selection of possibilities, then it marks the end of fundamental physics as we know it, turning it from an explanatory science into something akin to a grand descriptive catalog. The final metaphor of music, woven throughout our cosmic journey, is now transformed. Is our universe a single, perfectly composed symphony, a unique masterpiece of mathematical law, where every note is precisely placed, every chord predetermined by an overarching score? Or is it merely one random, fleeting note, a transient melody in an infinite and eternal cosmic cacophony of 10 to the power of 500 possible tunes, most of them lifeless and discordant? The question remains, shimmering in the cosmic dark, leaving us to ponder our place within this vast and mysterious cosmic landscape.